In the last video, we looked at a mature Type 2 civilization of the civilizational range scale. If you haven't seen the previous videos on this topic, do check them out. The link is provided for you in the description below. Today, we will be looking at the next step from a fully mature Type 2 civilization. So let's dive right in and explore some of the defining characteristics of an immature Type 3 under the civilizational range model. Zubrin believes that interstellar travel is the holy grail of astronautical engineering. The challenge is daunting, but the rewards are potentially infinite. For example, distance is the biggest challenge that a civilization must overcome in order to become starfaring. So, any mature Type 2 civilization that has conquered its entire stellar system and is ready to expand beyond must really consider inventing or innovating spaceflight technology that could support long-distance interstellar travel. This is because distances to even the nearest known stars are tens of thousands of times greater than those to the furthest planets in our solar system. To put this into perspective, the distance from the Earth to the Sun is roughly 150 million kilometers, or 1 astronomical unit, or AU. Planet Mars to planet Neptune all fall between 1.5 to 30 astronomical units, with Pluto at about 39.5 astronomical units. In comparison, the nearest known stellar system to us, Alpha Centauri, which is a triple star system, is about 4.3 light years or 270,000 astronomical units. Now that is quite the jump in distance. But currently, humanity has managed to speed up its fastest spacecraft, Voyager, to about 17 kilometers per second using multiple gravity assists from the 4 outer giants of our solar system. But as fast as this may seem, it would still take more than 79,000 years for Voyager to reach Alpha Centauri. So if such a probe had been launched from Earth the day Homo sapiens first set foot in Europe, it would still have another 30,000 years to go. Moreover, the problem is not just the vast distances between stars. It is also the fact that there are virtually no supporting resources along the way, such as sunlight or any other form of fuel that could be utilized for such long journeys. For this reason, many people believe that interstellar travel may be impossible without the exploitation of exotic or fantastical physical phenomena such as wormholes, space warps, cosmic strings, and so forth. However, for Zubrin, while orders of magnitude more difficult than interplanetary travel, interstellar travel is fundamentally feasible using currently understood engineering approaches. So what are these approaches, and how can humanity or any other mature Type 2 civilization overcome these challenges and advance to an immature Type 3 status? Well, there are a few possibilities that Robert Zubrin suggests in order to advance to a young starfaring Type 3. The first on the list to becoming starfaring is our very own chemical propulsion systems. The idea of our current hydrogen-oxygen rocket systems accomplishing interstellar travel may seem absurd, but it may not be all that bad. According to Zubrin, the maximum possible exhaust velocity of our current rocket is 5 kilometers per second, but the maximum practical velocity increment that can be delivered by a rocket engine to a spacecraft is about twice the exhaust velocity, giving a final push of 10 kilometers per second. With this speed, reaching the Alpha Centauri system would take approximately 135,000 years. But this is without considering the multiple gravity assists we could use to speed up our spacecraft, similar to what we have done with the Voyager spacecraft before. Using the gravity assists from the outer giants and the Sun, we could achieve a departure speed of 110 kilometers per second, reducing the travel time to get to Alpha Centauri to only about 12,300 years. Now that is quite an improvement, but it gets better. Zubrin believes that if we pushed our engineering to wild extremes along with numerous carefully planned stages, we should be able to achieve a final departure velocity of 175 kilometers per second or 7,700 years to arrive at Alpha Centauri. This, he believes, is the limit of chemical rocket technology. So to use this method of traveling to nearby stellar systems wouldn't be an ideal choice for humanity, as it would require many human lifetimes to complete just one mission. Naturally then, we must come up with something better. One way to obtain faster speeds would be to turn our attention to fission propulsion systems. In the past, there have been several proposals for nuclear fission-based rocket systems such as Project Orion or the nuclear saltwater rocket proposed by Zubrin himself. The idea behind Project Orion was pretty simple. Use a series of atomic explosives behind a rocket ship to push it to extremely high speeds. But of course, the risks associated with this are high as well. For example, one wrong explosion could evaporate the entire ship within seconds. Or a lethal dose of gamma rays could kill the entire crew on board. Perhaps this is why Project Orion was halted in 1963. In contrast, Zubrin's nuclear saltwater rocket dissolves fissionable materials such as uranium bromide in water as a salt and uses a similar method of detonation as chemical combustion rocket systems. But because the uranium is watered down, the exhaust velocity achieved by this method would be about 3,000 kilometers per second, or 1% the speed of light, similar to Project Orion, but without the need for mass-produced nuclear bombs. Now, since a spacecraft can generally be designed to obtain a change in velocity equal to twice its exhaust velocity, starships driven by such systems might be able to attain 2% light speed, allowing Alpha Centauri to be reached in about 215 years. But that is not all. An immature Type 3 civilization would be able to develop perfect fission drives that are capable of accelerating up to 8% light speed, reaching Alpha Centauri in just about 54 years. But even if we mastered fission drives, the amount of fissionable uranium-235 or plutonium-238 needed to fuel such systems would be enormous. So a civilization of this caliber might explore a more potent source of energy for their starship propulsion. Nuclear fusion is a much better alternative when it comes to interstellar rocketry with high exhaust velocity. Not only can a fusion reaction propel our spaceships with more power, but it also produces energetic neutrons, which can be used to produce power on board. There are several designs for these fusion propulsion systems. For example, the National Ignition Facility is a laser fusion system that can use a set of high-powered lasers to focus on a very small pellet of fusion fuel, thereby heating, compressing, and detonating it. There are other alternatives to this that require no lasers or bombs, instead relying on large magnetic confinement chambers to contain a large volume of reacting thermonuclear fusion plasma. Zubrin predicts that this type of system would be used to produce fusion power in the future, using deuterium and helium-3 as fuel. Along with advanced engineering methods, we or any other Type 3 civilization could theoretically produce an exhaust velocity of over 26,400 kilometers per second, or about 10% the speed of light. This would allow a one-way trip to Alpha Centauri in no more than 43 years, which is quite an improvement from the 54-year trip using the fission propulsion systems. But even 43 years could be a very long time in terms of the human lifespan. So can we do better than this? Zubrin definitely thinks so. While D-helium-3 may be one of the best sources of fuel found in nature, there is an artificial material that is much better. It is called antimatter, and we have been able to create it in labs. Antimatter is a mass with the charges of the subatomic particles reversed. So in ordinary matter, electrons are negative and protons are positive, while in antimatter, electrons are positive and protons are negative. This causes matter and antimatter particles to be attracted, which results in total annihilation, transforming their combined mass into energy in accordance with Einstein's famous formula E equals mc squared. So if we could freeze antihydrogen gas and use this material as fuel on a starship, annihilating it with ordinary hydrogen to produce energy, a single kilogram of antimatter annihilating with a kilogram of ordinary matter will release as much energy as 40 million tons of TNT. The maximum theoretical exhaust velocity of an antimatter rocket would be the speed of light. But of course, in practice, nothing can travel at the speed of light. But this method is far more promising than any other mentioned so far. A system called a photon rocket that could use antimatter and matter annihilations as fuel is said to attain anywhere from 50 to 90% of the speed of light. This means that a spacecraft of this caliber could get to the Alpha Centauri system within 5 years. Although it would seem like 3 years to the crew of the ship due to the effects of relativistic time dilation. Now that would be pretty impressive for any civilization to be able to achieve. Apart from these methods, Zubrin also considers light sails and magnetic sails. Although very cheap and effective, these methods are best used without any crew on board since they rely on simple sail designs to be pushed by man-made lasers, sunlight, or solar winds. But as we already know, it is simply not enough to send small probes to nearby stars such as Alpha Centauri to be considered an immature Type 3 on the civilizational range scale. An immature Type 3 civilization is one that is capable of traveling to its nearby stellar systems to colonize and extract all the useful resources. So what happens when humanity or any other mature Type 2 civilization starts to conquer its nearby stellar systems? How will they advance from here to become a fully mature Type 3 civilization? And what can a mature Type 3 civilization even accomplish? Well, that is a discussion best left for another time. If you enjoyed this video, do leave a like, share, and subscribe to our channel for more content like this. Will humanity ever advance to this level? Let us know your thoughts in the comment section down below. Until then, we'll see you in the next one.